Today's lesson is going to focus on some properties of alkanes. When we look at some properties of alkanes, there are a couple things we need to keep in mind. One is that alkanes are hydrocarbons and organic molecules, which are all covalent in nature. Okay, so when we have covalent molecules, we learned this in grade 11 chemistry, that they can be classified as either polar or non-polar. And when we are dealing with hydrocarbons in particular, so, alkanes and any of the families that you're going to see in this particular booklet, all hydrocarbons have either carbon-carbon bonds, which have a difference in electronegativity of 0, okay, because carbon and carbon, when we subtract off those values, we get a 0 value. Or we have a carbon-hydrogen bond, if we have a hydrocarbon, and the difference in electronegativity there, when we do the math, and carbon is 2.5, I think, and hydrogen is 2.2. I can't remember off the top of my head, but I do know that the difference in electronegativity between those two atoms or elements is 0.35. And this gives us nonpolar bonds. We know that if you have nonpolar bonds in your molecule, the overall shape of your molecule is also nonpolar. So there are no dipoles on these molecules. And this is very important to keep in mind because it means that the attractions between the molecules will be weak because we only have nonpolar molecules which have the weakest forces of attraction in between them. So organics, because they are covalent, we don't really talk about ionic properties here. We know that ionic compounds tend to have highest boiling points and higher melting points. They have very strong attractions between the ions, but we're not dealing with those molecules here. They're all covalent. And so as a result, we want to be aware of the polarity. So this is an important point for you to remember, that all hydrocarbons, and actually the majority of organic molecules, are nonpolar in nature. How does this translate to some properties? So what we're going to do is we're going to focus here on boiling point. Okay, we can talk about melting point as well, but sometimes with melting point, there's some irregularities in the trends, just simply because you're dealing with a solid and the way that the solids form in terms of the molecules and the attractions. It's a bit different than boiling point. So we're going to focus on boiling point, and we can also look at state over here as well. And what we notice is that the first 4 alkanes, so methane, ethane, propane, and butane, are all gases at room temperature. And this makes sense when you look at the boiling points. Okay, so you'll see there that nothing is above 0 degrees C. So that tells us that everything is in or below 0 is the boiling points of these. And this is really incredible. Like, think right here. Okay, the boiling point of methane is -164. This is extremely cold. Okay, very, very cold. We can't even begin to understand how cold that temperature is. But there is still enough thermal energy at -164 that you can separate methane molecules away from each other and give them some distance and put them in the gas phase as opposed to the liquid or the solid. And the trend carries on, and you'll notice that the boiling points start to increase as we move down this chart in particular, which is following most of the order of our first 10 alkanes. So we see methane, ethane, propane, butane, pentane, hexane. We're missing heptane here, and we're missing nonane, but that's okay because the trend would be the same. As we increase the number of carbons, we notice that the boiling points increase, and then the states start to change as well. We move into the liquid state. So why does this happen? Why do we notice that the boiling points increase as we increase the number of carbons and hydrogens in the chemical formula of these alkanes? Well, we have to recall what kind of forces of attraction are going on here with dispersion forces. There are no dipoles, okay? So remember this. These are not polar molecules. There are no dipoles in nonpolar molecules. But what does happen is on average, our molecules and their electrons are equally distributed. Okay, so right here you can see that the electrons are sort of, equally dispersed over the atom. And then at any given point in time, these electrons will start to clump up to one side of the structure. Okay, so you'll see this here. I'm kind of shading in over this purple. And when the electrons start to move around and clump up on one side of the atom, they will become slightly negative for a split second. Okay, split second. The other side of the molecule, because there are no electrons over there, becomes slightly positive for a split second. And what this does is on a neighboring molecule, such as this one next door, this region of negativity is going to repel the electrons. It's going to push them away to the other side of that neighboring atom, where this will become negative. This side will become positive. And then you get this very, very brief attraction setting up between your atoms that lasts for a split second. And then what happens is those electrons totally redistribute themselves, such as this, okay? And then they move around, they spread out, and then perhaps, we can see this scenario play out again, where they clump up on one side of the molecule. Notice it's a slightly different location. And this just goes on and on and on and on. So because these attractions right here last for a split second, you don't need a lot of force or energy to split these molecules away from each other. So when we have something like methane, okay, who has just one carbon and 4 hydrogens. So again, maybe the electrons are going to all clump up on this side of the molecule. This side becomes slightly negative. This side becomes slightly positive. Then when a neighboring molecule of methane is coming nearby, it can sense this region of negative charge over here, and it's going to repel its electrons and force them to go to the opposite side of the molecule due to repulsion. This side will become positive, and then you get this attraction happening right here between molecules. This is what we call a dispersion force. When you have more atoms and more electrons, so for example, propane, let's say. So here's a propane molecule. I'll just put the hydrogens in like this. Now what happens is two things. You have more electrons. So maybe all of your electrons clump up, let's say, to this side of the molecule, okay, and this becomes negative, the other side becomes positive. Then when you have a neighboring propane coming nearby, again, it forces these electrons to repel and go to the other side of the molecule. This positive area causes there to be an attraction between the two neighboring molecules. The other thing that can happen is that sometimes, and I'm just going to get rid of all of that, sometimes instead of all of the electrons clumping up to one side of the molecule, you might actually notice that some of the electrons clump up down here, let's say, and maybe some of them clump up over here or over here. And what happens is the bigger your molecule, you're going to get more unequal or more dispersion, is basically what it is, of electrons that will create small little mini dipoles all throughout the molecule. And that will attract a neighboring molecule in a few more locations. So this is why when the number of carbons, okay, so when your number of carbons increases, then your boiling points are also going to increase because you have more electrons and more parts within the molecule that can be attracted to a neighboring molecule. And now it requires more energy in order to separate these electron attractions or these dispersion forces. Sometimes when we are talking about organic molecules, we can talk about the impact of branching on boiling points. So for example, here are two molecules that are what we call isomers of each other. And the reason that they're isomers is that they have the exact same chemical formula. They have the formula of C6H14. And so what's happening here is they have an equal number of electrons. And when they have an equal number of electrons, we cannot argue that one molecule has more electrons than the other, and this is why, there'd be a stronger dispersion force between the molecules because of these extra electrons, and this is why the boiling points change. That does not apply here. So what is the impact of branching? So if we talk about hexane, for example, and we draw out a hexane molecule, so that's 5, and we see this structure with our hydrogens placed all around. Again, we know what's going to happen here. These electrons will either clump up in one side of the molecule, or maybe I'm going to put them over here. So I'm going to have some electrons here, and I'm going to put some electrons over here. So I'll distribute them a little bit more. We know the other side is going to become positive because the electrons have moved. When there's a neighboring hexane, and I'm not even going to put the electron or the hydrogens in right now. Again, you're going to have repulsion of these electrons pushing down. Okay, so I'd have some negative charge here, and same thing here. They'd sense the electron charge on the neighboring molecule. This side becomes positive, and then you get your attraction setting up here between your molecules. When you have branching, so for example, something like 2,2-dimethylbutane, I'm just going to show you. So I'm going to have carbons above and below on carbon 2. And what I have now done is I have just changed the surface area of my structure. Okay, so I've gone from a more linear shape right here to a more circular shape right here. And that change in surface area now reduces the contact points where those electrons can clump up and where there could be attractions between neighboring molecules. So for example, maybe the electrons are all kind of hanging out here for a split second, okay? And this area becomes positive. Well, when I have a neighboring 2,2-dimethylbutane next door like this, again, electrons are going to be repelled in the neighboring molecule. This becomes positive, and then I get the attraction between the molecules right there. When I have this surface area being changed, there's two things happening. So less points of contact, but I also have these branches in the way. Okay, so they're sticking out. And those branches actually cause like a barrier to get these molecules as close together as possible. So this is something called steric hindrance that actually reduces the attraction between molecules, because you think of them like, a big branch, like if you're trying to, branches on a tree, right? They get in the way. And if you were trying to stack these close together, it's not going to work. Okay, because these branches get in the way and they cause there to be like a natural distance that has to happen between molecules, which lowers the attraction, lowers the dispersion forces. So branching always reduces the boiling point for two reasons. Surface area is going to get reduced, and steric hindrance of those branches gets in the way, and the molecules can't be attracted as tightly as they'd like.